going to be complex ion equilibrium. So in this situation, what we're doing is we're talking about the equilibrium associated with either the formation or the dissociation of a complex ion in an aqueous solution. So let's just go back and remember what we mean by complex ions. This is the very first thing that we did at the beginning of chem dynamics. So what we had, if you'll recall, is a combination of a metal ion, typically a transition metal ion, and a ligand. And remember what's happening here is that the ligand is forming a bond into the D-deficient electron metal ion here. So we're going to form bonds by donating electron pairs into the iron ion. And when we do that, what we're going to make is this very stable complex ion. And these are the very same complex ions that we talked about at the beginning of this course. So, as I mentioned to you, we can set this up as an equilibrium situation. So normally, when we look at this, we do it from the standpoint of the formation of the complex. We're making the complex. Now, when we do that, this equilibrium constant for this type of reaction will be called a formation constant, a Kf, because again, we are forming the complex from its component ions. Now, if I set it up in this manner, what I'll see is that the Kf, according to the law of mass action, is going to be the concentration of the complex ion divided by the concentrations at equilibrium of the component ions that we have. And since we know that complex ions tend to be very stable relative to their component ions, we'd expect the Kf values to be very large, and indeed they are. The Kf for this particular complex ion reaction is 1.0 times 10 to the 31st, a very large K value. So again, that tells us that at equilibrium, the position of the reaction at equilibrium very much favors the formation of the complex ion over its component ions. Now again, Kfs are important because when it comes to looking at complex ions, these are the reactions and the equilibrium constants that we can find in the tables. So if I need to find a characteristic K for the formation of a complex ion, it'll be in terms of a Kf, and we'll find it in a table, very much like we can find Kas, Kps, and KSPs. All right, so there's another way to think about this. One thing we can do is form the complex ion, and if we form the complex ion, we see that's going to be governed by a Kf. But what if I take a complex ion that I've already made, and I want to then dissociate that into its component ions? I could look at that reaction as well. So in this particular case, what I would do is I would just take my original reaction and I would flip it. So what I'll end up with is a reaction that looks like this, where I start with the complex ion and I let it dissociate into its component ions. So this particular kind of reaction is characterized by a Kd, which is called a dissociation constant. Now, if I want to calculate a Kd, I can do that with knowledge of a Kf, because again, all I did was I flipped my Kf reaction to get to the Kd reaction. So what I'll find now is what used to be products now become reactants and vice versa. So what we have here now are the equilibrium concentrations of the ions in our law of mass action divided by the equilibrium concentration of the complex. Now, since all we did was flip a reaction, we can calculate a Kd from a Kf by just taking the inverse of the Kf. And when we do that, in this case, I get a value of 1 times 10 to the minus 31st, a very small number. And that's exactly what I would expect, because again, we know that the complex ion is going to be very stable compared to its component ions in solution. So as a result of that, this equilibrium should lie very much to the left or the reactant side. So that would suggest a very small value of K. So whether or not in a problem you use a Kf or a Kd depends upon the wording of the problem. Are we forming a complex or are we dissociating a complex? So the next example that we want to look at, which is going to be example number 10 in your handout, will give you a chance to see that. All right, folks, so let's now take a look at this particular example problem. Again, this is example number 10 in the chapter 19 handout that I gave you. So the question asks, what is the equilibrium concentration of silver ion when 0.01 moles of silver nitrate are dissolved in 1 liter of 2 molar NH3? And we're going to assume here there's no change in volume when I add the silver nitrate to the ammonia solution. The other piece of information that's important to you here is I tell you in advance what the complex ion that we are making is going to be. Now in some problems we may not actually do that. So for example, if you knew that I was making a complex involving a metal ion, in this case the silver ion, and I need a ligand, okay, and I tell you in this case the ligand is going to be ammonia, you could go to the KF table and you could find the complex ion that's going to be made with silver ion and ammonia. And the option that you find will be this one right here. It's going to be the silver ammonia 1+ complex ion. All right, you could look up a KF for that. But again, in this case, I'm going to give you that information. So ultimately what we find here is we're just going to have a collection of silver ions, and we're going to have some ammonia molecules running around into solution. So what we need to do first is we got to make this complex, okay? So really this is a two-step problem. In the first part of the problem, we need to make the complex, but then in the second part of the problem, we then have to go and redissociate the complex again so that we can now figure out what the free concentration of silver ion is going to be. That's what we're trying to find here. All right, so the first thing that we have to think about is that silver nitrate is just a soluble salt. So it's really nothing more than a good source of silver ion and nitrate ion. All right, so in this situation, I'm just going to show you the dissociation. It's just a 1-for-1 dissociation here. When it breaks apart, I'm going to get silver ion and I'm going to get nitrate ion. Now, we have to ask which of these is the important ion. Now, could nitrate be of interest here? Not really. It's not going to be the ligand. Okay, so for all practical purposes, nitrate here is just going to be a spectator ion. So I know I can get rid of it. The things that I care about, again, are going to be the silver ion and the ammonia. Those are the two things that I have to put together to form my complex ion. All right, so what does this tell me? If I get a dissociation, and I'm starting out with 0.01 moles of the silver nitrate, by my mole relationships, I'm going to get 0.01 moles of the silver ion. All right? Now, also, at this point, what we can do is we can set up a table now so that we can show the actual formation of the complex. So we need a balanced chemical reaction, and then we need a table to go under that. All right, so let's move on over here so we can see how the complex is actually being formed. Now in this case, we can see here's the silver ion, here's the ammonia, and I'm making the silver ammonia complex over here. Now I'm going to use an ICF table here. And the reason I'm going to do that is because I want to drive this equilibrium 100% to the right. And the reason for that is because the KF is a large number. So again, just to remind ourselves, the KF is 1.6 times 10 to the 7th. So we saw back in the equilibrium chapter that if we have a reaction that has a really big K, what do? Well, we let that reaction go 100% to the right first, and then what we can do is we can reverse it and let it come back a little bit. And that's what we want to do here, because ultimately what we're trying to find is the concentration of the free silver ion in solution. All right, so let's look at this from the point of view of a simple ICF table. So I'm looking for a limiting reactant here, and I see one. It's going to be 0.01 moles of the silver ion. All right, so I've got 0.010 being lost. Now be careful here. When you ask yourself how much is lost, all right, we have to also be aware here that the stoichiometry is now 2 to 1. All right, so now I'm talking about the loss of ammonia, which happens to be my excess reactant. So I have to remember here now to double the amount of my limiting reactant that I'm going to lose in terms of the ammonia. So this becomes minus 0.020. Again, be careful of the stoichiometry. Now, if we convert this to the amount of the complex ion that we make, we're going back to a 1-to-1 stoichiometry here, so that's going to be positive 0.010 moles of the complex. All right, add down as normal. We can see again the limiting reactant is going to be our silver ion. We're going to have 1.98 moles of the ammonia, and I'm going to form 0.010 moles of the complex. All right, so there's my ICF table. That's what I get when I run this reaction 100% to the right according to my limiting reactant. But again, the question's asking me for how much free silver ion I've actually got at equilibrium. That's this, okay? And from the ICF table, I have none. So now what I got to do is I got to run this reaction back in the opposing direction a little bit so I can generate some silver ion. So now what I'm going to do is I'm just going to flip the reaction, and my Kf now becomes a Kd. I'm using a dissociation constant here. And again, we're going to convert everything to molarities because we've got an ice table here, but that's easy because I've got 1 liter of total solution. So I take my moles from my ICF table and divide by 1. So what we see is the moles just become molarities here. All right, so in that sense, my complex ion starts out to be 0.010 molar. I'll put a big M there just to remind ourselves that these are molar concentrations now. My silver ion, what's that? Oh, that's 0 molar. Don't have any of that. And my ammonia, that's 1.98 molar. Again, we're not at equilibrium because now what we have to do is bring this reaction to equilibrium by allowing it to run to the right. Right? Because my Q is 0, I need to make some silver ion. All right, so again, watch your stoichiometry here in the C line, folks. I'm going to go minus X there, I'm going to make X there, and I'm going to make 2X here. All right, now let's add down as we normally would. And we got 1.98 plus 2X. All right, so now all this has to go back into the law of mass action. But again, now we're using the dissociation constant. So how are we going to set all this up? Products over reactants raised to their respective powers. So I've got an X there for the Ag1 plus. I've got a 1.98 plus 2X here. That's for the ammonia. Oh, but watch out. I have to square that because I have 2 in front of the ammonia. All that's going to be divided by 0.010 minus X. And all of that has to be equal to the Kd, which is 1 over the Kf. So let's see, what did we say the Kf was? That was 1.6 times 10 to the 7th. So that should be a very small number, right? So this is a nice thing because now my K has become a very small number, so now I can simplify my math accordingly. So now we know that we can get rid of additive and subtracted X's, again, because our K is now small. So now our math gets fairly easy. We can see that we have X times 1.98, and I have to square my 1.98. All that divided by 0.01. And that's going to equal to 1 divided by 1.6 times 10 to the 7th. So now this is very easy to solve for X. So now if we solve this all out for X, provided I did my math right, X turns out to be 1.6 times 10 to the minus 10th. Now what does that correspond to? Again, that's going to be my X over here in my ice table. And that corresponds to the equilibrium concentration of the free silver ion in solution, and that's exactly what the problem asked us to get. So I'll put a molarity there and say that that's equal to my equilibrium concentration of the silver ion. And again, you're going to notice that's a very small value, and that's exactly what we would expect, because again, the silver ion is a reactant over here, and the Kf is large. It's also the limiting reactant, so at equilibrium, we'd expect to see very, very little of it in solution. So we'll practice more with this tomorrow. So we'll see you next time.